with video number 3 for electric current. Now, we're going to try to explain to you an electric circuit using the first 2 videos. So you're going to use that vocabulary: voltage, Coulomb guys, current, resistance, and we'll talk about power a little bit. And then we'll talk about the 2 formulas only in explaining how this works. So you're not really going to need the formulas to be described in your video. All right, so we're going to start. I'm going to flip over so you're looking at the circuit, not me. And this is an electric circuit, and you're not going to have anything like this really fancy. I can take the switch and flip it and the light bulb goes on. What you're going to have is something really crude, but it's going to have the same components. Number 1 component is a power source, or energy source, I should say. Sorry about that, wrong vocabulary. The energy source creates voltage. Remember, voltage is the energy of a Coulomb guy. So how do we get that? Well, in this case, it's a battery. You could use a battery, you could use a generator, you could use a potato. So it just depends on what you're doing, but you have to describe for us in your video how that source was created. In this case, a battery is in a factory. It goes into a really strong electric field, and the negatives are inductively pushed from the positive side to the negative side within that battery. So there's work done on the battery pushing electrons from the positive side of the battery to the negative. Now, in static electricity, we learned that is inductive charge, which is what we use. That's why you did static first. And we polarize the battery. So there's a positive side and a negative. So remember, gold positive, blue negative. That's going to be important. Okay, now, once the field or the charge is created, it creates what we call an electric field. Positive side of the field on this side, negative side on that side. And what's going to happen is when I connect this, light bulb's going to go on. Now, the light bulb in that formula is the resistor. So we did some work in. It's like lifting a rock up, and then we dropped it, and the rock hit something, and that did work. Okay, so the work in this particular case is lighting a light bulb. So the Coulomb guys come out of the negative side of the battery. They go through the light bulb. Then they go through the switch, and then they go back home to the positives. Now, they don't go through the battery again. When they get over here to the positives, they're done. They've done their job. There's now no more energy in that Coulomb guy. He's just sitting over here, neutral, happy camper. It's like I went to work, did my work, and went home. That's what you're going to describe. Now, the current, I, is actually the other way. Okay, think of a river. And the river, the field, or the current flows from positive to negative. We call that an electric field. It goes from positive to negative. Now, why are the Coulomb guys going the other way? Well, because they're negative. So they do the opposite of what you would expect. Negative velocity means I turned around and went backwards. Negative acceleration means I went from growing to shrinking. Well, negative in electrical terms means I'm going to swim against the current. So little Coulomb guys swimming upstream to get back home, and by the time they get there, they've done all their work. Now, I'm going to show you a couple other things that could happen. Okay, I could add a light bulb to this mix, and we call this a series circuit because it's going to do a couple different places of work. So I'm going to come out of you're going to describe this. Let's pretend you make a series circuit and you're going to explain this. You're going to say, I got a battery, which creates the electric field going from positive to negative. That's the current flow. The negatives are going to come out and swim upfield, but this time we're going to do work here and here. And when I collect it, you can see the lights aren't so bright anymore. That's because 1.5 volts that are in this use 0.75 here and 0.75 there. In other words, the work in has to equal the work out, just like every other system we've done. Now I can change this. I can make this what we call a parallel circuit. Parallel means I have a choice. It's like going to school. Today you have a choice. You can you can go to one class or you can go to a different class. But you're only going to do your work today in one class. Today is science day, so you're going to your science class and that's it. Now in a series class schedule, you have to go to every class all day long. You don't get a choice. You have to do them all. So when I turn this light on, you're going to see it lights up pretty good again. That's because my Coulomb guys are either going to take this path and go home, or they're going to take this path and go home. They're going to do 1.5 joules of work here or 1.5 joules of work there. Remember, voltage and energy are the same thing. So when I'm saying joules, voltage, same thing. Okay, this is a parallel circuit. Now, another thing I could do is I could go back to my series circuit. So I'm going to do that. I'm going to put a light bulb right here, and I'm going to put a line there, and I'm going to hook up another battery. Now this time I'm going to hook the battery in what we call series, okay, which means that I'm going to take my Coulomb guys and make them go this way, do work on this battery, 1.5 volts. So when they get to this battery, they're at 1.5. We call that a reference voltage. It's very similar to saying, okay, I'm 1 meter off the desk, so I have 1 meter of potential energy, but you could always move it over across the ground and all of a sudden you have 2 meters of potential energy, gravitationally speaking. Well, it just depends on where you started, over the desk or over the ground, to determine how much potential you have. Well, here's the ground. We got to the desk, and then we went from the desk up. So what ends up happening is I now have 3 volts of electrical potential. Again, you're going to describe the circuit, so I'm going to leave with my electrons, go through this light bulb. I'm going to go through the switch, go through another light bulb, and then back down. So each battery is each lighting 1 light bulb. Now, if I really want to fire this thing up, I could do this and put it back into that parallel situation I had earlier, except this time I'm going to do it with 3 volts of electricity. So this is going to predict how. What do you think is going to happen to those light bulbs? We now have created 1 volt, 1.5 volts, 3 volts. We're going to run it through this one or that one. So predict what's going to happen in your brain. And voila, you are correct. We get the brightest of bright bulbs. 3 volts going through this one or 3 volts going for that one. So some important things that I need to hear in your presentation to me. You've got to tell me where the work in was, the source of energy at the beginning. They did work on these batteries in a factory, 1.5 joules per coulomb of work. Then we did the current, goes the opposite way of the flow of electrons, and I want you to tell me the flow of electrons go from the negative side of the battery, blue, to the positive side, gold. And I want you to tell me this is where the resistance is, so this is where the work's being done. And most importantly, I want you to tell me that the work you put into the system is the work that came out of the system. So we're going to do the same experiment with pickles. We're going to do the same experiment making a motor work, and we're going to use generators and electrical current right out of my house. This one obviously is with batteries. So good luck with your project. I got 2 examples for you coming here in a second.